Hello students, today we are going to see the topic 8051 timer programming using assembly and C. In this video we shall see basics of timer and counter and timer programming and a basic of counter programming, that too in C. Through this video let us try to get answers for the following questions. First of all, what is a timer and use of a timer in 8051 microcontroller? Then what are the different types of timers in 8051 microcontroller? Let us get some basics about timer and counter programming. Whenever we see timer, these are the images that we get. Timer basically it represents a clock. We can observe different types of timers are there here. Here is an alarm clock. So in this slide, again, we have timers in the appliances that we use at home, which are nothing but the embedded systems. So after looking at these images, we might know how the timers are used and what is their usage. What is a timer? As I just told, a timer is basically a clock that controls the sequence of an event while counting in fixed intervals of time. It is also used in microcontroller. This timer is used for producing precise time delay. And secondly, it can be used to repeat or initiate an action after or at a known period of time. This feature is very commonly used in several applications like your alarm clock. Hmm. An example could be setting up an alarm which triggers at a point of time or after a period of time. Next, we come across two words, timer and counter. Timer is basically a clock which is used to measure time intervals, and counter is it's a device that usually counts the number of times a particular event or process has occurred with respect to a clock signal. So it is used to count the events that are happening outside the microcontroller. This in this slide we can see the differences between timer and counter. So timer is it's a clock which is used to measure time intervals, and the timer uses the frequency of internal clock and it generates delay. The maximum count rate is 1 divided by 12 of the oscillator frequency. Whereas counter, it is a device that stores the number of times a particular event or process occurred with respect to a clock cycle. It is used to count the events happening outside the microcontroller. Counter uses an external signal to count the pulses, and the maximum count rate is 1 divided by 24 of the oscillator frequency. Why do we need timers in the microcontrollers? Uh, Basically, the timers are required to generate delays, and for generating delays, we have two ways. One is using software, another one is using hardware, the timers. Using software, if you want to generate time delays, then you need to write loops, for loops and all those things, and you can generate the delay. And if you want to generate it using the timers, you can do it so again through programming. But when you generate a time delay using timers, it will be more precise compared to the delay generated using software. Here the value of a counter increases by 1 every time its corresponding action or event occurs. So basically, the counter has to count the number of events. Its value is increased by 1 every time an event occurs. The timers in a controller are inbuilt chips that are controlled by special function registers assigned for timer operations. We shall see what are those in the later part of this video. These SFRs are used to configure timers in different modes of operations. As I said, there are two possible ways of generating time delays. One is using the loops, another one is using the timers. So the delay generated using timers is more precise compared to the first method. 8051 timers. The basic 8051 microcontroller has two on-chip timers that can be used for both as timers as well as counters. The both timers may be controlled, set, read, and configured individually. So the 8051 timers have three general functions. First one is keeping time and or calculating the amount of time between events, that is uh, generating time delays. Second one is counting the events themselves, and the third one is generating baud rates for the serial port. This picture shows the two timers of 8051. So they are timer 0 and timer 1. In timer 0, the timer 0 is a 16-bit register, and since we know that 8051 has a 8-bit architecture, hence this 16-bit register of timer 0 can be accessed as two different registers as low byte and high byte. The low byte register is called as TL0 and the high byte register is referred to as TH0. So in this diagram you can see the structure of timer 0. The bits D0 to D7 represent the low byte, that is TL0, and the bits D8 to D15 represent the high byte, that is TH0. Timer 1, it is similar to timer 0. It is also a 16-bit register, and as I just told, it can this just like timer 0, it can also be accessed as low byte and high byte. And here you can see in the diagram the structure from D0 to D7 the bit, it is represented as TL1, which is the low byte, and from D8 to D15th bit of the register it is represented as TH1, which is the high byte. If we have TH0, it means it's a timer 0. If we have TH1, it is timer 1. Similarly, TL0 means timer 0, TL1 means timer 1. The value of 8051 timer registers increases by 1 every time a timer counts. Timer takes a time period of one machine cycle to count one. And what is a machine cycle? Machine cycle is a unit that refers to the time required by the microcontroller to execute instructions. This means that the maximum number of times a timer can count without repetition is 2 raised to 16, because 16 is the number of bits in the timer register, and that will be equivalent to 65,536 in decimal. So the maximum allowed counts in value of timer register can be from 0000H to FFFFH. So this is the range that we can have for a timer of 8051. Let us see the next slide. So this is uh, again it explains the same thing, that is timers are T0 and T1. They have been divided as TH0 and TL0 for timer 0, and for timer 1 it is TH1 and TL1, each of 8 bit. We can access them as 8-bit registers, or we can access them completely as T0 or T1 also. 8051 timer issues. So while we are using the 8051 timers, certain factors have to be considered. For example, whether the timer is to be used for timekeeping or it has to be used for counting, and whether the source for time generation is external clock or the controller itself, and how many bits of the timer register are to be used or left unused. So we have to keep all these points in mind, and then we have to work with the timers. How a timer functions basically. So this process we have to know before knowing the further details. First thing is all the registers of timers are loaded with some initial value. If no value is provided, the default value will be taken as 00. The value of the timer increases by 1 after every machine cycle. So, uh, after every machine cycle, the value whatever is there in the timer will be incremented by 1. So one machine cycle duration is 1/12 of the crystal frequency attached to the controller. We know about this. For example, if the frequency of the crystal is 12 megahertz, then the frequency of the timer will be 1 divided by 12 into 12, so it will be 1 megahertz. And hence, time period, we know time period is always equivalent to 1 divided by frequency. Hence, if you take 1 divided by 1, you will get 1 microsecond as the time period. Similarly, for the crystal frequency of 11.0592 megahertz, which is the common crystal frequency, the operating frequency of timer will be 921.6 kilohertz. How we got this? We have to take 1 divided by 12 into this 11.0592. So we'll get this value. And to get the time period, we have to divide this value by 1. So 1 divided by 921.6, we'll get 1.085 microseconds as the time period. If no initial value is loaded into the timer, it starts counting from default value, that is 0000H. This rollover concept. Rollover concept is an important concept. When the timer reaches the maximum value, that is FFFFH, if further it after this value, it cannot have any larger value above this. So it reloads to the initial value, that is 0000H, and this process is known as rollover. Switching from FFFFH to 0 is known as rollover. So the rollover is communicated to the controller by raising a flag corresponding to that timer. It may be timer 0 or timer 1, and the flag bit is TF0 for timer 0 and TF1 for timer 1. So these are the overflow flags. They are part of the TCON register, which is a special function register for timers. And these flags must be cleared by the software every time they are raised. Then the timer may terminate updating register values after a rollover or continue with its operation as the necessity. This image shows the rollover concept. So we have some initial value in the timer. Every time the value is incremented. So once it reaches the maximum value, you can observe until that the flag value is 0. A general TF value is taken. It may be TF0 or TF1. Here it is 0. It means it is low. Once the value crosses the highest range, that is FFFFH, a rollover happens, and when a rollover happens, automatically the flag value is set to 1. Starting or stopping a timer. So this is also very important. It can be, there are two means of doing this task. That is, we can start or stop a timer using hardware means, as well as we can perform it using software means. So if you are doing it using software means, then you need to use the bits TR0 and TR1 of the TCON register. So TR0 is for timer 0, TR1 is for timer 1. If you set timer TR0 to 1, it starts timer 0. If you are writing it in assembly, you need to write set B TR0. Then if you take TR1 equal to 1, it means it starts the timer 1. Similarly, to stop, you have to make it as 0. Configuring a timer. A register called T mode, which is the timer mode register, is used for configuring the timers. It means we can select different modes of timers. We can start or stop the timer. We can also configure the timer, like we can use it as a timer or we can use it as a counter. So this is the structure of the 8-bit T-mod register. Here you can see uh, 4 bits are divided for timer 0 and timer 1. The lower nibble is for timer 0 and the upper nibble is for timer 1. The lower nibble and the upper nibble is exactly same. It contains the same 4 bits. So Tmod is an 8-bit register in which the lower 4 bits are set aside for timer 0 and the upper 4 bits are set aside for timer 1. In each case, the lower 2 bits are used to set the timer mode and the upper 2 bits are used to specify the operation. So here the lower 2 bits are M0 and M1. Here also M0 and M1. These 2 bits are used for setting the timer mode, whereas these 2 bits are used for different purpose. Let us see. So first let us see about M0 and M1. We can have these 4 pair of values for M0 and M1. So when M0 and M1 are both 0, it is known as mode 0 and it is a 13-bit timer mode where 8-bit timer or counter will be there and THX with TLX as a 5-bit prescaler. So it is a 13-bit timer mode. The range is different for each mode. When the value is 0, 1, that is M1 is 0 and M0 is 1, it is mode 1 and it is a 16-bit timer mode. So complete 16 bits are used. So the range is higher compared to the first mode. Then for the next set of values, that is 1 0, if M1 is 1 and M0 is 0, it is mode 2. It is known as a 8-bit auto reload mode. We shall see mode 1 and mode 2 in detail because they are the most commonly used modes. Last one is when both the bits are 1, it is known as mode 3 and it is a split timer mode. It is not so much used mode. So we are going to see mode 1 and mode 2. We got to know about the lower two bits M0 and M1 and their purposes. Next bit is C by T, okay. C cross T. Here it is this bit is used to select a timer or a counter. For example, if this bit is equal to 1, then uh, it is set for counter operation. So if this bit is equal to 0, it means it is for the timer operation. Then the gate bit. So it is the gating control when set. Basically, this bit is used to start or it is used to enable the counter timer. To enable the counter, as I told earlier, we have two means, either hardware and software. So if the gate bit is set, it means we are trying to use the hardware means to enable the timer. So it means the timer or counter is enabled only when intex pin is high and TRX control pin is set. Both have to be high. So when the gate pin is 0, if the value of this bit is 0, it means we are using the software means to enable the timer, and in that case, the timer is enabled whenever the TRX control bit is set. So TRX, we have just come across it. TR0, TR and TR1 bits are there, which are part of the Pecan register. Using that bit, we can set the timers. This is another register, Tcon. Uh, Tcon register is again an important register. It is also an 8-bit register. Here, the lower nibble is set aside for interrupts and the upper nibble is set aside for timer. So we'll in this concept we'll concentrate on timer and we shall see about interrupts in the later videos. In the upper nibble, we have 4 bits. You can observe TF1, TR1, TF0, TR0. So by now you might now easily understand that TF1 may be for timer 1 and TF0 may be for timer 0. Similarly, TR1 is for timer 1 and TR0 is for timer 0. So TF1 is a timer timer 1 overflow flag. Okay. So this bit is set by the microcontroller when timer 1 overflows. And TR1 is timer 1 run control bit. So when this bit is set, timer 1 is turned on. Here we have, these are for timer 1. Similarly, TF0, it is same like TF1 except that it is for timer 0, and TR0 is same like TR1 except that it is for timer 0. And these 4 bits are for interrupts. Next, timer mode 1 programming. So this I will discuss in the next video. Thank you.